Okay, today we are going to look at section 7.2, which is going to start us on the path to inference, which is going to kind of be the theme of all of second semester. It starts to really get real in chapters 8, 9, 10, 11, 12. Chapter 7 is kind of like a warm-up into those. So in chapter 7, we're going to be given information that we wouldn't typically have in real life. They're only doing that so that we can get used to the mechanics of how things work. So in real life, it says right here, in real life, we won't know the actual values of the population parameter. So a parameter, remember, is anything dealing with the population. So it could be a mean, it could be a standard deviation, it could be a proportion, but it's relating back to the population. In real life, we won't know those values. We're going to be estimating those values, and we'll take a sample, and based on the sample, we'll estimate the population. But in chapter 7, they're going to tell us those values, which is a little unrealistic, but we just have to kind of go with it so that we can get the idea behind these things figured out. So we are going to be dealing with problems primarily that involve means and proportions. We're going to start by talking about proportions today. Okay. So how do you know if it's a proportion problem? You're literally going to see the word, like, what proportion of US adults have watched Star Wars: The Last Jedi? Or what percent of the adult population attended church last week? You're going to see percents, and you're going to see the word proportions, and that'll be a huge clue that it's a proportion problem. Okay, so what we've talked about in the past are binomial distributions, and when we checked BINS, remember that acronym BINS, when we checked that, if all of that held, then we were allowed to use these two formulas here for our mean and our standard deviation. What statisticians have found is that if these two things are true, if n remember is the sample size, and p is the population proportion. If you multiply those two things, n times p, and they come out to be a number greater than or equal to 10, and if you take n times 1 minus p, and it comes out to be greater than or equal to 10, if those two things happen, then a binomial distribution becomes approximately normal. And that's important to us because when things are a normal distribution, we get to use z-scores. I showed you that in online with like a little applet. When we were talking about the penny distribution, this is the population of pennies was skewed to the left because there's less pennies in the older years, like in the early 1900s. And there's more pennies in the 2000s, if you remember that. And then what we did is we took a sampling distribution, and the sampling distribution ended up looking normal. That's kind of what's happening here, where the binomial distribution turns out to be approximately normal. But the key is these conditions have to hold. So that's where we're getting at. So here's kind of the origins of the formulas we're going to be using. P hat is our sample proportion. And we would get a sample proportion by taking the number of successes divided by the number of things we have in our sample. So let's say we were doing the proportion of people who hike. I would take the number of people in my sample. Maybe there's 100 people in my sample and maybe only 30 of them hike. And so my sample proportion would be 0.30. That's the idea behind the stuff in the red box. Now, if I took many, many sample proportions, this would be the symbol of that. I would be finding the average of all of my little sample proportions. So I would have the average of many samples divided by my sample size. Now, this mean becomes NP. That's going back to my previous page for binomial. Mu of x equals NP. Okay, so I'm just replacing that here. So mu of x, oh, I gotta grab my pen. Mu of x equals NP over n, and then you'll see that the n's will cancel, so I just get a p. Now this is a formula that we are going to be using when we're talking about our sampling distribution. We talked about this, how if I make a sampling distribution, and each little dot is my little sample proportion, and I have a whole bunch of these sample proportions, whole bunch of p hats, and they make a normal curve. Okay, all of these are little sample proportions. The mean of my distribution, the center of my distribution, so the mean of all of these little p hats, should be a good approximate of what the true population proportion is. So like when we were talking about pennies, we were talking about sample means and how if it's unbiased, the mean of all of my samples should line up with the true population mean. It works the same way with proportions. So the red line is the mean of all of my sample proportions. That should equal the population proportion. They should line up if it's unbiased. And that's actually what this says right here. Remember, your statistic is unbiased if it is equal to the true parameter. So remember, statistic deals with your sample, and parameter deals with your population. So I want my p hat to be an estimator of p. So this is my sample proportion. I want a whole bunch of sample proportions to be a good estimator of my population proportion. So, in any case, this formula right here is something that we are going to be using a lot. That's the formula for mean, the mean of my sample proportions. Here's the formula for standard deviation of all of my sample proportions. And this is the symbol that we use. Now, this is the origination of the formula, but we can just hop right to the formula. So if I want my standard deviation of my sample proportions, I'm going to take the square root of P. Again, P was the population proportion. Times 1 minus P divided by N. And N is, again, the sample size. You will be given those two pieces of information. Okay. So, in order to use those formulas, we have to check some conditions. So, when we are doing a problem, we're going to need to both state and check our conditions. And this is true on the AP test. According to their rubrics, we have to both state and check. So the first condition that we have to state and check is the population more than 10 times our sample size? So that's the question we have to ask. Is our population more than 10 times our sample size? Now, we can abbreviate that and here's what it would look like. Is our population, which is capital N, more than 10 times our sample size, which is little n? Okay, so again, capital N is our population size, and little n is our sample size. We have to be very careful of our symbols. Capital N is very different from little n. So our population size could be the whole United States, and our sample size could be 500 people. So this is stating our first condition. You can state it using words. Is the population more than 10 times our sample size? Or you can state it using the abbreviation. Is capital N greater than 10 times little n? This is what's called our 10% condition. The book likes to refer to it as the 10% condition. If this condition holds, it verifies that we can use our standard deviation formula. Okay? The second condition is what I showed you a few pages ago when I showed you how a binomial distribution becomes a normal distribution. Here's our second condition we have to check. Is our sample size times our population proportion greater than or equal to 10? And is n times 1 minus p also greater than or equal to 10? So again, remember, little n is our sample size, and p is our population proportion. If both of those work, then we can use a normal approximation. And that is a good thing, because then we will be able to use z-scores. So, if both of those conditions are met, then we get to use these formulas. Mu of p hat will equal p. So that means all of our sample proportions, the mean of our sample proportions, I'll write it out. The mean of our sample proportions will equal the true population proportion. And then our standard deviation for our sample proportions will equal the square root of p times 1 minus p over n. These are our two formulas we're going to need so that we can calculate z-scores and use our whole z-score z-chart and all that to find probabilities. So the first condition allows us to use the standard deviation, and then our second conditions allow us to use a normal approximation, which then lets us use z-scores. So we have to state and check those conditions before we can get to these formulas, before we can use z-scores. So we're going to practice all of this, putting it all together. All right, so here's our first scenario. How well can BSM students identify Iraq on a map? BSM enrollment is roughly 1,100. We're going to take an SRS of 100 students. Now, this is where it gets kind of funny. The stats fairy says that 30% of BSM students can identify Iraq. Now, in real life, we wouldn't know that. That would be something we're trying to approximate based on samples. But in Chapter 7, we're given information that we wouldn't typically have in real life, just so that we can get the mechanics down. So all of that is saying that our population proportion is 0.30. Our sample size is 100. Our population is 1,100. We're only talking about BSM students. So our population is BSM students. Okay. So we're going to state and check our conditions. So I'm going to color code it. I'm going to state it in red. Is the population more than 10 times our sample size? Another way of saying that is capital N more than 10 times little n. So we're going to now check that. Okay. 10 times our sample size of 100 is 1,000. And we know that BSM has more than 1,000 students. So this checks out. Our population is more than 10 times our sample size. Then the next condition we have to check, state and check, is n times p greater than or equal to 10 and n times 1 minus p greater than or equal to 10. We're going to check those. N is our sample size, 100. P is our population proportion of 0.30. When we multiply those, we get 30, and 30 is greater than or equal to 10. So that works. And then we're going to check this condition. Our sample size of 100 times 1 minus p, which is 0.30, is 70, and 70 is greater than or equal to 10. So both of those work. So now that this first condition worked, that means we can use our standard deviation formula And because the second condition worked, we get to use a normal approximation. So what are our mean and standard deviation? So the mean of p hat is equal to p, and we were told that p is 0.30. The standard deviation of p hat is equal to the square root of p times 1 minus p over n. And again, p is 0.30 times 1 minus 0.30 all over our sample size of 100. If you put that in your calculator, you're going to get 0.0458. And I like to keep as many decimal places as possible with my standard deviation, so that when I plug it in my z-score formula, my z-score is as accurate as it can be. Okay, so there's our mean of 0.30 and our standard deviation of 0.0458. So now we get to the real questions. We're going to find the probability that our sample proportion is less than 27%. That means, in other words, the probability that less than 27% of our sample can identify Iraq correctly. So in other words, we're finding the probability that less than 27% of our 100 BSM kids in our sample can identify Iraq correctly. So our conditions checked out on the last page. We found that our mean was 0.3 and our standard deviation was 0.0458. And now we know that it's approximately normal. All of those conditions worked. So now we can use z-scores. This question up here, if I write it out in symbols, is asking us to find the probability that our sample proportion is less than 0.27, 27%. I'm going to do some side work over here and, going to use my side work to get my z-score. So 0.27 minus the mean of 0.3 divided by my standard deviation of 0.0458. When I type all that in, my z-score will be negative 0.66. Remember to round to 2 decimal places. Okay, so then over here, my next statement would be that I'm trying to find the probability of z being less than my z-score of negative 0.66. So I go to my z-chart now, and I look up negative 0.66 on my chart, and since I'm doing less than, whatever I look up is my actual answer. So when you look it up, you get 0.2546. 25.46 is our answer. That's the probability that less than 27% of our BSM students in our sample can identify Iraq correctly. You can always draw a picture of the scenario to see if things look right. So this z-score was negative 0.66. So we're talking about here, and we're trying to find the probability of being less than that. Okay, so that seems to check out. All right, next one we're going to look at is we're going to find the probability that our sample proportion is within 2% of the true proportion. Okay, well, what is the true proportion? The true proportion was 0.30. Remember the stats fairy said so? So we want our p hat to be within 2% of 30%. Okay, so I'm going to write this here. The true proportion was 0.30. What range would be within 2% of that? So 2% below 30% would be 0.28, and 2% above 30% would be 32%. So my sample proportion is going to be somewhere between 0.28 and 0.32. Again, from the previous problem, our mean of our sample proportion was 0.30, and our standard deviation of our sample proportion was 0.0458. We need that information to find our z-scores. So I'm going to find one z-score using 0.28. So 0.28 minus the mean divided by the standard deviation. That z-score is going to be negative 0.44. And then I need to find my other z-score for 0.32. Again, minus the mean of 0.30 divided by the standard deviation of 0.0458. And when we type that in, we get positive 0.44. So that means that we are trying to find the probability of our z-score being between negative 0.44 and positive 0.44. So when we use our z-chart, we look up the bigger z-score first, and we get 0.6700 minus, and then we look up the smaller z-score second, and we get 0.3300. And when we subtract those, we get 0.34. So the answer to our question is 34%. And again, if you were to draw a picture, we've got a z-score of negative 0.44 and a z-score of positive 0.44, and we're finding that probability of being in between, and that's about 34%. Okay, so a lot of the stuff is, let me just go back real quick. Here's the general idea. You got to check your conditions, state and check them, and then you get your formulas, for mean and standard deviation. Then it's z-score work. So you might have a z-score problem where it's less than, you might have z-score stuff where it's in between. If you have a greater than, remember you do 1 minus whatever you get when you look up on your chart. Then the only other kind of problem you're going to see is something like this. This is asking, what should our sample size be so that our standard deviation goes less than 0.03? This would be a question you would ask yourself before you even get started, because you might want to figure out what would be a good sample size to take. And you would want a standard deviation to be low so that your graph, if you want to think of it that way, is less variable, more compact, hopefully a little bit more precise. So it's kind of a good thing to have a smaller standard deviation. So in this case, remember that our p was 0.30. So if I plug in this standard deviation into the equation and I plug in 0.30 for p, I can then solve for n, because remember n is the sample size. So we're going to solve for n. Okay, so what we would need to do is we would need to square both sides to get rid of that square root. And when you square both sides, 0.03 squared would be 0.0009. So then the square root was taken off. I can multiply 0.30 times 1 minus 0.30, and I'll get 0.21 over n. And then if you want to cross multiply, it would be 0.0009n equals 0.21. So to get n alone, we would have to divide by 0.0009. So n equals 233.33. Now here's the thing. If n equals 233.33, then my standard deviation will be exactly 0.03. But the question wants my standard deviation to be less than. So how we fix that is, if our denominator is bigger, that'll make our overall answer smaller. So the denominator is n. So if we make n a little bigger, the overall answer, which is the standard deviation, will get smaller. And that's what we want. We want our standard deviation to be less than. So we're going to round up. So round n up. So I'm going to use, instead of 233.33, I'm going to use 234 people. If I round up that denominator a little bit, my overall answer will get smaller. Okay, so always round up. I have that right here. So, you might be wondering which region is Iraq. Looking at your map, do you remember what Iraq is? Okay, if you don't remember, you could look it up online. All right, so you have some homework you can work on, and then that should be it for today. All right, have a good one.